Yeah, so welcome everybody to the very first lecture that I give in my life on post-quantum cryptography. So it's great that so many people showed up. You know that from my other videos. Here's the overview, right? We have 4 sub-chapters today. First, I want to give an overview about post-quantum cryptography. This is essentially it's 2 slides, two tafeln, 2 blackboards. I think it's quite interesting. Then we do simple hash-based signatures, whatever that is. This is also short. And this is all easy and enjoyable, right? And the third one is tough, right? We talk about Winternet's one-time signature, so this is kind of the main part of the lecture, right? I'm going to say multiple times, wake up, wake up, wake up, right? Okay, so this is somewhat challenging here. And security of Winternet's one-time signature is easy. Okay, so 4 chapters. 3 enjoyable ones, 1 tough one. Okay, get ready. Okay, so where do we start? So we first give an overview about post-quantum cryptography. So this is chapter 1 here. Now gives it a different name. I call that quantum computers, which we will abbreviate by QC, quantum computers, and cryptography. This is what we are really interested in. So this is not a lecture on quantum technology. Okay, so first chapter. Okay, so first, and if you drop out of the IT security program this evening, just remember what I'm putting on this blackboard. So this is very interesting beyond studying IT security or cryptography, right? So first, very important, okay? Namely, large scale means like quantum computers that are large enough that you can do nice things with it. Large scale QC do not exist at the moment, okay? So you can't go to eBay, you can't go to MediaMarkt and buy a quantum computer for $10,000, right? You can't even buy it for $10 million, right, or euros, right? But, you know, Pünktchen, but might exist in 10 to 20 years. Okay, so this is a weird situation. They don't exist. We don't even know whether they will exist. And there are 2 question marks here. What does might mean? Maybe, vielleicht. And what does 10 to 20 mean, right? And both of them are vague, right? Die sind vage. So if I knew that, I could make money with this, right? So there's, roughly speaking, there's a huge international community consisting of experimental physicists, Physiker, and quantum algorithm people. We have Professor Walter, for instance, here in your Studiengang. He also offers courses for you. They're intensively working on that. So they're easily billions of euros spent every year on building large-scale quantum computers, right? We don't know whether people will succeed. A lot of very smart people that know way more about this than me say 10 to 20 years is a pretty good guess. That means there's a pretty good chance they might come into existence in our lifetime, right? Okay, so this is very important to bear in mind. Okay, so, and now a big question is, which is really the motivation for this course here. What can an attacker do with large scale quantum computers? Fragezeichen. Okay. So where do we do that? I think I'm going back to this here. And what I'm going to show you now, there's zero mathematics behind it, but the statement I'm going to give you now, the facts are very cool and important. Okay. So as you know, when we look at crypto algorithms, they come in two flavors, right? What are the two big families of crypto algorithms?
The symmetrical and asymmetrical.
Excellent, very good. We have symmetric algorithms. And asymmetric algorithms. And spoiler alert already, the impact that quantum computers that might or might not exist at some point have on these two families are hugely different, right? So what you can do with quantum computers is hugely different, heavily depends whether you look at AES or at RSA. Okay, so symmetric ciphers, what's a good example? What is the example? What is the most popular symmetric algorithm? AES. Okay. AES, and we say with n key bits, okay? We need n in a minute, right? And n is, it's nowadays, in all the cipher kind of the same. You run them either with 128 or 256 bits, right? Here's a quantum computer attack against AES. You can do a key search in, 2 to the n. This is brute force attack AES. Does everybody know that? Otherwise, you have to drop out of this program, right? This is very important, right? N-bit block cipher normally, unless it has mathematical weaknesses, you get a 2n security guarantee, right? Everybody awake? So this is, if you have AES 128-bit key, we need 2 to the 108 steps. With quantum computers, we only need the square root of that, okay? So this is, and we know that from, 10th grade, right? Mittelstufe. This is n over 2, right? So what is the interpretation of this weird formula is quantum computers have the key length, effective key length of AES, right? So what is it if the normal AES has a key search needs 128 steps? What do we need with quantum computers? How many steps is this if n is 128? Do you want to punch that into your iPhone? If n is 128, which exponent do we get? 64, very good. You can verify, 128 divided by 464. I'm joking, right? So that means AES 128 with quantum computers, at least the big O, asymptotic complexity is only in quotation marks 2 to the 64, okay? This is Grover's algorithm. How do we fix this? Der kleine Kryptograph, how do we do that? So there's an attacker who can effectively halve the bit size of the key. How do we get out of this situation? Double the key size, right, okay. So, n should be at least 256. What about AES? Is that a problem for AES, the situation here? No, because there is AES 256. You remember that, right? And why is there AES 256? Because of this. And this is a really nice, it's not a coincidence. This is, the AES process started, I think, in 1997. So how much is this? This is like 28 years ago, a long, long time ago, right? This attack, Grover's attack, barely existed then. NIST, the National Institute of Standard Technology, already knew about it, and that is the reason why I said we need 256 because of this attack. Okay, so here, this is why 256-bit AES exist. If you just have conventional brute force attack, we're fine with 128, right? 256 you need if you're worried about attacks in 10 to 20 years. Okay, so if this were everything we need to know about quantum computers and crypto, the lecture would be over. We could go to the men's and have lunch, right? Unfortunately, it's very different here. So what are the example algorithms? There only 3 families, actually many more families, no, not many, there are more families, but there are only 3 families of asymmetric cryptography that's in use nowadays, meaning implemented in our browser, implemented in WhatsApp and Signal. This is RSA, discrete logarithm, and elliptic curve, ECC, okay? What can a quantum computer, what can we do with a quantum computer attack? And I have to switch to my second favorite color, red, completely broken, okay? That's Shaw's algorithms. If we have a quantum computer, it's very easy to break our end-to-end encrypted WhatsApp encryption because that needs elliptic curves for key exchange, okay? This is dramatic. This is why I used red, okay? This would be a catastrophe if quantum computers would exist at the moment. They don't. Once they exist, we're all in deep shit, right? So this is a real problem here, okay? So, what is the fix? Here it was easy, we could increase moderately, right? I mean, 128 is already not particularly long. Going to 256, who cares, right? Here you don't get away with increasing the key length, right? So even go, and the implementations that use RSA with about 10,000 bits, it can still be broken. This attacks that's behind it, these are cycle finding attacks, they're incredibly powerful, right? So we lost, right? We lost. So what we need here is new public key algorithms. Okay, and what we need public key algorithms that are not vulnerable against these attacks. And we're not talking about these attacks. I think Professor Michael Walter is teaching a class on that. He's definitely teaching a class on quantum computing in general. So we need other public key algorithms that don't belong to the RSA family, don't belong to the discrete logarithm family, and don't belong to ECC, right? And now, one time, you have to still pay attention. These new types of public key algorithms that are not vulnerable against quantum computers have a really fancy name, namely post-quantum cryptography, okay? So this is post-quantum yeah.
So we know that we need post-quantum cryptography for solving the problem with asymmetric algorithms we have right now. But how sure are we that there will not be or already exists in the intelligence community a similar approach for symmetric?
Very good question. Essentially, we don't. But but it's similar to here. Does anybody remember what is the attack method we would use against RSA? What do we need to do to break RSA? Yeah. Factorization, integer factorization, right? We have to factor. This is what people have been worried about since 1977, right? Almost 50 years, right? Are there better factoring algorithms around? We don't know, right? We don't have a guarantee. But it's still a good question. But what's happening is there's this worldwide community. They look at attacks such as what we're doing today here. They haven't found any. So there is, people, of course, looking at these alternative ones. People, at least at the moment, they seem to be confident that you cannot attack them with quantum computers, right? I should say quantum computers, I don't know very little about it. They're very special. They're more like special purpose computers. They're not generally programmable. That you can use quantum computers to break these 3 families, which are really 2 families, as you know, right? Because ECC is also discrete logarithm, is more or less a coincidence, right? So it would be a pretty big coincidence that we came up with a new post-quantum public key algorithms, and then really by chance, again, you can use quantum computers for that. It's quite limited what you can do with quantum computers. You cannot use it to program your favorite TikTok app or whatever you want to do here, right? And you can't run Excel with that, whatever, right? So these are not general purpose type of algorithms. But it's a good question. It's a good question.
Implications for symmetric.
Oh, no, for symmetric. Oh, I'm sorry. But here, again, I know very little about it, but allegedly there's even a proof that you can't, at least with respect to key search, because this is a key search algorithm, you can't become better than square root of. Okay. I thought you were talking about this. Good. Now we want to, this is the one time today where I'm using a slide. You know, I hate using slides, as you know. What I want to give you, so a lot of people are working on that, including here in Bochum, it's the hotspot, right? This is one of the leading places worldwide where people work on public key cryptography. Not me, but two of my favorite colleagues, Eike Kills from Ruhr-Uni and Peter Schwabe from the Max Planck Institute, they're working on that. So I just want to walk you through the slide here. It's very easy. This is the state of practical post-quantum cryptography algorithms, right? What are the two things we do with public key cryptography? And we did that this semester. So we started at the end of semester 1. We can digital signatures with that, and we can do encryption, and KEM stands for key encapsulation. Sorry. Okay, So on the right-hand side, this KEM is key encapsulation. This is a fancy version of what we called in semester 1 key transport, right? You can use RSA for exchanging keys and digital signatures. There's a huge amount of research going on with coming up with these type of quantum-resistant cryptography algorithms, right? Right now, we are kind of the worldwide community, mainly scientists, but also government agencies and standardization agencies. They're converging to 3 or 4 type of algorithms, namely lattice-based, code-based, and hash-based. And yes, they are a good way of advertising my book. So these are all covered in here, right? There's a fourth one, multivariate. Do I talk about that? No. There's a fourth one, which is a little less popular, but it's also seems also sound, multivariate, right? And what you can see, typically, they're kind of special. Typically, you can, with one of each of the algorithms family, you can essentially do one thing. With lattice-based, you can, is the one exception where you can do digital signatures and key transport, key encapsulation. Code-based, which is the oldest one, you can only do key encapsulation. And with hash-based, which are we going to do today? So we are on the bottom row, hash-based, you can only do digital signatures. Okay, why do we do that? Because it's fun, right? Hash-based is fun, we just is hash, so that's what we're doing. Next year, there's a good chance we're going to add either lattice-based or code-based to that, but let's start easy, okay? So, and again, if you plan to drop out of the wonderful Bachelor Master IT Security this evening, this is all you need to know. Okay, so we're done with chapter number 1 of today. So this is kind of a summary what you need to know. But I hope most of you will stay in the program, right? So, okay. Anyhow, hurrah! Where is the? Hurrah! We're done with this here, yeah. And by the way, this is also very important. Oh, danke, Julian. Very important thing. So the name is post-quantum cryptography. I think he was coined by Dan Bernstein, famous cryptographer. It's a beautiful name. It's very misleading. I mean, the first time I heard that, I thought this is quantum, right? This is Star Trek, Raumschiff Enterprise, right? This is not, right? Post-quantum cryptography does not use quantum effects for computation. These are essentially normal, boring algorithms that happen to be resistant against quantum computers, right? Okay, so, and I don't have any numbers. I assume tons of people misunderstand that, right? Okay. Okay, so second chapter, what is the second chapter? Simple hash-based signatures. So this is kind of we want to work ourselves towards, drauf zubewegen, towards hash-based signatures, right? Okay. Simple hash-based signatures. Okay. So first we start with going back, what are conventional signature algorithms, right? So this is like a little refresher. Basic DS, basic digital signatures, right? E.g. RSA or ECDSA, elliptic curve digital signature algorithm, which we did not do here in the lecture, but it's in the book. Okay, and you all know this. This is very simple, what I'm going to show you. We did that, I think, 3 weeks or 4 weeks ago. So we have Alice, we have Bob, and we also going to need Oscar for the discussion. And this is, of course, the prime example of a public key algorithm, right? So we have, surprise, surprise, Alice has a car private, her private key, but she also has her public key. And the public key is public, so it can be sent over. You used to find mine on my website, right? I used to have my PGP public key on my website, so everybody can see that, including Oscar, including Bob. Then Alice signs with a private key, and we had a big discussion about that, right? And this is the beauty of public key cryptography. It's really great. Only one person who knows the super secret private key, 2048-bit RSA key. Only the person who knows that key, it might reside on a smart card, might reside on your smartphone. You can use that for signing, let's say, a digital contract. Let's call the signature S. So we have a signature algorithm. And again, we talked about that. We had El-Gamal digital signatures and RSA digital signatures, which this is our notation where we have the index K private on the message M here, okay? And this is going to play a role in about 10 minutes, right? So the signature algorithm needs 2 inputs, namely the private key, but also the message itself, right? The message might be a PDF digital contract, right? I'm buying this motorcycle or whatever, right? I'm buying that iPhone. What Alice sends over is this pair M and S, right? The message and the signature. And now the kind of the cool thing is Bob can verify using the public key. And there's some verification algorithm which uses the public key, and the verification also needs M and S as input, right? So you verify the signature relatively to the message. Very complicated question. No, very easy question. What are the possible outcomes of the verification process? How many bits of information do we get out here? Yeah.
1 for it's right and 0 for.
Yeah, true and false, exactly, 1 bit. Very easy, right? We might get a 2048-bit number out. What we're really looking for is true or false, right? Very good answer. Okay, that's it. And then we talked at great length about security services. And that was actually big motivation when the way we introduce digital signatures here, that we approach them from the security service point of view. So authenticity, meaning, and we always have to, honestly, even in the literature, they're not very super exactly defined, right? Authenticity, what we really mean here is sender authenticity, meaning can Bob be assured that this message is coming from Alice? Yeah, so authenticity is Bob with respect to Alice, right? You can also achieve that with symmetric. We're going to talk about that in a few weeks. Then we have message integrity, which we just called integrität, integrity, meaning can Bob detect changes in this thing? So let's say if Oscar replaces m by m prime, what do you think? Will that be detected by Bob? Yeah. Of course, right? You could throw that away if it didn't work. Because then you don't have m, you have to place m prime in here, but the s doesn't fit m prime, right? So that, yeah, we have integrity. And then the big thing, and I talked about it for like 15 minutes in this video, right? This weird thing, Nicht-Zurückweisbarkeit, right? Non-repudiation. Non-repudiation. I don't know whether do people recall that we talked about it, even if you can't? Yeah. There was this car with the car sales, right? So here was, that's the issue. Can Alice later claim this M is not really coming from me, it's coming from Bob. Bob generated that, right? Bob was the car dealer, that was the setting, right? And that's kind of the really nice thing. We also get this, and this has to do with the fact that you have to sign with the private key, and with the public key, you can only verify but not sign, right? So that was the big thing. Okay, so weit, so gut. So that is kind of somewhat of the baseline, right? So we now the goal is, the quest is, can we achieve that with post-quantum cryptography? Because the problem is RSA, maybe you can break RSA in 20 years, right? You go to eBay, buy a quantum computer for $1 million or maybe $10,000. You break RSA, and then all these nice properties get lost, right? Okay. So now, start to buckle up, langsam anschnallen. We are looking at our first kind of baby protocol, our first simple Versuch to build we're building our first post-quantum cryptography scheme. Everybody okay with this here? This was just repetition. If you didn't understand, you didn't pay attention the last few months, right? Which never happened to me as a student, of course, right? So I'm kidding. So, okay. So let's call that maybe naive. A naive hash-based signature. And why do we go to hash-based here? Because hash-based are essentially symmetric algorithm. So the best thing to attack, the best basic mechanism to attack hash functions, right? You know, SHA-3 that we did last week. The best way of attacking that is, again, only Grover's algorithms. We can only do the square root thing, right? So we have essentially more or less a guarantee that hash functions themselves cannot be attacked with quantum computers. That's kind of the basic idea why we do hash here. So if you wish, this is out of the three families of post-quantum algorithm, lattice-based, code-based, and hash-based, this is maybe the most conservative one, because the chances are extremely small that people will be able to break SHA-3 or SHA-2, whatever. Okay, so now, unfortunately, you have to wake up, right? So now we're doing some extremely simple things. So we're not doing, this is not elliptic curves, right? It's not elliptic curve group operation, some crazy thing. The math is extremely simple. What we're doing looks weird, right? Zu einfach, wahr zu sein, right? Too easy to be true, right? Okay. Namely, okay. So what Alice does, and we have Oscar. We don't really need Oscar, but let's just put him down here. Okay. So for the private key, Alice just picks a random number. Let's say a 512-bit random number, random integer. And this by itself is not surprising. Very often the private keys are random number, and then with quite a bit of effort we compute the public key. We do something similar. We do compute a public key, but not very weird, in an extremely simple way. Namely, we take a function r, and in a nutshell, the function f we take a function f and put r in, the random number. The function f is in practice a hash function. It's SHA-3. You know all the homework you did last night, right, for today? Or this morning, right? This is what you're doing here, right? So we need one, here the property of R is random, here the property, and this is going to come up over and over and over again in the next 60 minutes. This is a one-way function. The different properties that hash functions have, and the number one, which we call the Urbild resistance, right? The one-wayness is very crucial here, okay? Alice, not surprisingly, sends the public key over. Oh yeah, and we call this, I'm sorry, we call this P. Okay, you can also write it here. This is P for public, right? So, Bob has public here. Okay. Why don't we do that? Good question here. So, okay, so public goes over, so this is f of r. So if you were Oscar, without knowing any more details what's going to happen here, what would probably be a nice parameter to have for Oscar? Which variable would Oscar like to know? What do you guess? Yeah. Of course, right? It's a private key. Probably he can sign, right? Probably he can do a transfer in Alice names, transfer 1,000 euros in Oscar's account, right? So, okay, so he knows f of r. What does Oscar have to do to get from public to get R out? What is the mathematical operation here? What do we have to do? Yeah. No. Okay. This is a real-world attack, right? No. You're too advanced. Okay. Simpler. I'm looking for a simpler answer. Okay. What do we have to do to get R out of this f of R? How do we call this operation we have to do? Yeah. Invert, right? We have to the invert. Can we do that? No. That's the notion of the one-way function. You can't go back, right? Again, SHA-3, the topic of this week, of last week's lecture. If I give you the output, even if the input is only, let's say, 30 bits, you get a 512-bit output or whatever. You cannot go back. This is one way, okay? So this is just like a motivation why the general setup is maybe not as stupid as it looks. It gets really stupid now, okay? Because now we look at signing, namely, and let's look what we did here, right? We signed using the private key and the message. And buckle up, now comes something really stupid, and this is not going to work, right? But it has one really nice property, but I'm going to show you. We don't care about M here. Alice simply takes the private key and says this private key is going to be the signature. It seems, what is Christof talking about, right? This is stupid. It's pretty stupid, but it's not totally stupid, as you will see in a minute. So what? So Alice sends over her private key together with M, okay? So one thing, just if you like totally what's going on here, this is super stupid. One thing, all of these hash, what we're doing today, they're all called, where is it? Do you see the number 3? Winternet's one-time signatures, they're all one-time signatures, which is a very new notion. That means you can only use this R one time here, right? So you don't have to worry too much that Oscar knows this R here at this point, because we only use it one time, right? Okay, so this. And then the idea is if let's say I do one bank transfer per day, then I generates 365 of them, and then I could do bank transfer every day, for 1 year, for instance. So it's maybe not that horrible. It's still weird what we're doing here, right? So please don't leave, right? I didn't come up with that scheme, right? So verification. So this is normally, we want to do verification using the public key on M and R. Am I inconsistent here? I'm a little bit inconsistent, okay. R, M, right? But here, what he can do, Bob, is kind of interesting. He can take R, which was the input to this function, right? F is SHA-3, right? This is in my book. This is on Wikipedia. Everybody knows F. Everybody knows the one-way function here, right? This is no secret. It means he can hash R, and now he can check whether this R is equal to the public key. Okay? That's this point. Okay? And I know this seems really, this can't work. And again, you're right, it can't work. But there's still a little bit of hope. The basic idea is not totally crazy what we're doing here. Namely, if this checks out, what does he know? Can somebody make this intellektuellen Sprung, this mental jump here? What does Bob know if this checks out? If this checks out here? Assuming he knows P is car public coming from Alice. Okay, what does, yeah?
So I think he's able to tell that the first message was from Alice.
It was coming from Alice. Nobody else, even I'm, famous applied cryptographer. I can't do this here, right? I cannot send R out here, right? So once Bob gets R, that message, he knows that must come from Alice here. Everybody is very quiet and looks, this is weird, right? And now let's maybe do like somewhat systematically, let's look at the security services here. Erstens ist authenticity, and this is exactly what you just said here, right? It means sender authentication, meaning is this message really coming from Alice? Yes, I mean, do this Gedankenexperiment. What Oscar, Oscar would love to do this, right? Oscar would love to send R, M prime here, right? He cannot come up with an R here, right? He doesn't know R. We had the discussion before. For R, he has to invert SHA-3. Good luck, right? This is not going to work, right? So he can't do that. So authenticity we have, the other two things not, right? And I know everybody is looking, what is he talking about, right? And I'm going to resolve, ich gebe Ihnen recht in 60 seconds, right? Namely, we look at message integrity. Namely, forget about this here, can Oscar do this? Can he replace the 10 euro transfer into Oscar's account to 10,000 euro transfer? Absolutely. Why is that? What we should do, we should verify R together with M. This is a verification equation here. Where is M here? There's no M here. You know what I'm saying? So this is why it looks so stupid. Are people a little bit relieved? No, right? A little bit, right? So this is why it's basically, it's mostly a stupid idea, but there's some hope, right? So we do not have integrity here, right? So this is, and non-repudiation, this is actually kind of a repudiation, a Grenzfall, like an in-between thing. So and I looked in literature what they're saying. I would say basically not, because could a judge say that R, M is coming from Alice or Bob? I mean, Alice is only the person who can generate that, but Bob could also manipulate the message here, right? So I would, which is not the case here, by the way, right? Because Bob could still, if this is a contract, right, a legal contract, also Bob could replace M by M prime, and it would still check out, and a judge, a neutral third party, cannot distinguish between M and M prime, right? So I think it's safe to say we don't have non-repudiation. Okay, yeah.
Why can Oscar not just entirely replace the public key? So would one be created from an own private
Yeah,
key?
yeah, that's what, yeah, yeah.
And the base
Yeah, 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 yeah.
private key in the second term. And that
Yeah.
kind of defeat the whole purpose, right?
Absolutely. So what we implicitly, and that's what you meant before too, right, with an attack, right? You're absolutely 100% right, except I'm a bad teacher, right? So the implicit assumption is that this worked correctly. So if Alice gets a P, and it's not the naked P, right? It's P, it says, I'm the public key of Alice, this is correct. So what you're assuming is Bob gets an incorrect public key. Is that right? Yeah. So but this is, yes, you're absolutely right. And yes, we spent the last week of this lecture on this very topic. You need certificates with that. So you need special mechanism to assure this here. Okay? But this is, and I know, Christof is too generous. He's too sloppy. No, so, this is even like basic, whatever we do with AES, right? When we talk symmetric cryptography, we always assume Alice and Bob have the correct symmetric key, right? So this is an implicit assumption, and yes, I should have written that down here. We assume that the public key is correctly distributed, right? And it's, again, this in practice, who has heard about certificates in web browsers? Just the term, everybody. This is this problem here. Right, you need certificates so that Bob knows he really has Alice's keys. So you need, again, digital signal for that. This is a story by itself. We do that in the very last lecture. It's lecture number 25 or so on YouTube. We do that, and then we have follow-up lectures in your ITS security program that talks a lot about network security and digital certificates. Okay, but excellent input. Good. So, shall we use that for, securing the nuclear launch command? No, of course not, right? This is stupid, right? But there's some hope. I mean, it's not bad that we can do authenticity, right? And then now what we're going to do, we're going to do an improved version of that and this, and now we come to the main part of the lecture, namely Winternitz. Now you really have to wake up. Yeah.
I think I got a little bit lost here.
Okay.
So Alice is signing a message, right?
Yeah.
The output of the message is that private key?
Yeah. So exactly. This is great. Great question. Yeah. Alice doesn't even use M at this point here. For any message, whether it's a PDF contract, whether it's an email, whether it's electronic voting, doesn't matter whether M is 1 bit or 1 gigabyte, we always use R, which is super stupid. And we're going to solve that now.
The output is R. Like the output of the signature algorithm is R? Or
The output of the signature algorithm is R. Very good. Signature is R, yeah.
that's why it's
Yeah.
okay.
Super stupid what we're doing here. Super stupid. We're going to fix that now. Ideale Einleitung for the next chapter 3. So chapter 3 is Winternitz 1 OTS. OTS stands for one-time signature, so, okay. So what we need here, and that's why your question was so good. The basic problem is up there, that the signature does not take M into account, right? No matter whether it's 1 bit, whether we vote for party A or B, or whether it's a long 2 megabyte digital PDF contract, the output is always stupidly R. That, of course, doesn't work. So let's fix that. Okay, so the goal is, signature that depends I'm worried about my space. I'm very bad. I'll continue here on M and K private. Okay. So example. Look at a baby message, 3-bit messages. So this is not a big PDF file. This is 3 bits, right? But once we understand 3 bits, maybe we can also go to 1 million bits. Okay, so 3 bits, right, can be 0, 0, 0, or 0, 1, 0. There are all kind of patterns possible. And you might have heard that in total, we can represent the integers 0, 1, 2, 3, 4, 5, 6, 7 with 3 bits, right? So if you take notes on your college block, you need 7 lines here. Okay. Now we look at the bits. So that's bit 2, bit 1, bit 0, and this is kind of 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, blah, 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 blah. I'm doing the 5 because the 5 we're going to use later as an example. This is binary system, right? So this is very basic here. You feel free to fill all of them. Okay, here the last column, the rightmost column is kind of a cool thing. What we're doing here, okay. So we say, and the goal is, we have 8 different values here for the message, and each message should get a different signature, which is exactly what we did not have here, right? Regardless of M, we always put out the same random number, right? Okay, so if the message is all 0, we do exactly what we did before. We say our signature, the signature is K private is R, okay? So again here, R is random, okay? So the private key is again a random number, 512 bits, whatever, right? Okay, now it's getting interesting. If the message is equal to 1, so it's a bit pattern 001, we hash this once with the hash function f here, okay? So this becomes this is always, what's my red chalk? So what you see here on the column, the signature is one-time hash functions. If the message happens to be the bit pattern 010, so the decimal 2, we hash 2 times. So we do f of r. And there's a shorthand notation, which is nice, namely f square of r. So this is not the algebraic f square we know from school, right? So this is not 5 squares equal to 25. This is a notation. Please apply the function have 2 times iteratively. Hashing once, hashing twice, okay? Blah, 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 blah. If we do it, for instance, if the m is equal to 5, then the signature is applying the hash function 5 times in a row. You take your message M, you put it into SHA-3. This is what you did this week, right? You get an output. The output you put again in SHA-3. You get another output. You do that 3 times, 4 times, 5 times. Yeah. What's that? feel free up to correct me anytime. I'm good at making mistakes. Okay, so blah, 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 blah. And then in the last one, if the message happens to be 111, you hash actually 7 times of R. And this also is public. Okay. Okay, so can people, you're looking, you're questioning what I'm doing? Or?
Does that not exponentially increase the runtime with larger messages?
No, it's oh yeah, I mean the messages get long. Yeah. But the output is on. What is the output of each of this operation here, except this one? How long is the output of each of this, row 1, 2, 3, 4, 5, 6, 7? How many bits do we get out? It depends on what, yeah?
Depends on the hash function.
Yeah, we only get the hash output. Yeah, is that worrying you? Yeah, this is not ideal. I mean, life is hard, right? So this is yeah. But again, alternative is the NSA break or the Russian Secret Service breaks in 10 years your messages, right? So right, yeah. No, the message overhead, that's a technical term, is not pretty here, okay? But all of that is going to change next week anyway. We're going to do something very cool with it. Okay, so I see still a lot of people that don't really trust what I'm doing here, right? There's kind of a nice graphical, there's kind of a nice graphical thing we can do with that. Okay, I like the next one, and this is, I did not invent it. This is kind of a natural way to depict that, to show that. Okay, so yes, this is. Basic mechanism. What I mean with basic mechanism, yeah. Sure.
So if M has a bit length of 7, the output is the same as if it has a bit length of 1, because FR is the same thing.
Yeah. No. So first of all, the input is over 3 bits, right? We talk at 3 bits, right? But I mean, you're right. But you only have 3 bits. The output is always whatever 512 bits, something pretty big, right?
But my question
Yeah.
is, M of the value of 1 is FR. There's like one time, it's the same thing. This is the way we rechnen.
Yeah.
Our private key.
Yeah, but no, the private key is this. That's how we berechnet the public key. But now the public key becomes this here. Okay. But stay with me for 3 more minutes. Okay. These are all good questions. Things will. Then again, this is. I like the next kind of graphical representation of what we're doing here. Okay. Another way of showing this right-hand column, which all puzzles us a little bit, right? We're all a little bit perplexed by this, right? Okay, there's a very nice way of doing that, right? So again, we look at this case. M is 101 in binary, or 10 in the decimal system. So we start, and it's great to have these blackboards. Car private is R, that's a random number. So what Alice does initially here, you see, we start. I did a little sneaky, right? I started with the private key and did all the stupid steps, and then said at the end, oh, this is a public key, which confused you, right? So of course, what Alice now has to do in the real world, start this and hash 1 times 3 times 7 times, right, to compute the public key. So what we want to show you, like kind of a graphical representation of the key generation. So you do this is F to the R. Then you apply F again, you get this F square of R, right? You do that, output is again put through a hash function. This is F hoch 3. Again F, this is F to the 4th. This is F to the 5th. nochmal f to the 6 and f to the 7th of R. And this is K public. Okay. So, and going from here to here, this is done by Alice, and Alice computes f to the 7th of R. Okay? Everybody with me? I like this better than the stupid table up there, right? This is kind of, oh, you do f function, f function, f function. This is what he meant, right? Okay, good. The really cool thing comes now, right? Stay with me for the next 2 minutes, right? So this is really nice. So, and this is just key generation. You have a question? Yeah. Yeah, but we also need the public key. That's why. Stay with me for 2 minutes. No, that was a perfect question, exactly. Because now, what does signing entail? Signing is, this wasn't super common here, right? The signature goes from, signature is here, right? So we do now, have to be careful. So this is done by Alice. This is signing. The signing part is kind of, we don't stop in between, but this intermediate value here, you know, Alice computes 1, 2, 3, 4, 5, 7 times this. Whatever she computed after the 5th times becomes the signature here. So this, for this M, the signature is f to the 5th of R. Okay. So this is, if you ask me, this is a nicer, I'm sorry, I'm going down. I'm going to put that back up again. This is a nicer way of showing this here. Okay. But the really cool thing is still to come. Okay. So to recapitulate, initially this is the key generation phase. Alice does key private and key public by iterating 7 times. What she computes on the way after 5 times becomes the signature. So right now, what's going on? Why does she even go here if she only needs it? But what is missing from this protocol? What is missing from what we've done so far? This is really the cryptographer, and you're going to have Eike Kills and Alex May, my colleagues. This is a 3-phase protocol. This is a key generation. This is here, right? Then you have signing is step number 2. Which step is missing here? What have we not covered? Yeah, over there. Verification. This is number 3. And that's what we're going to do now. You don't know what I'm talking about, right? Nobody knows in this room. Don't you worry. Buckle up. This is now the cool thing. Bob gets S, right? Together, what else? Bob knows S. Which other value does Bob know? Yeah. No, not the private key, but you're close. He knows F, and he does not know the private key, but he knows the public key, right? He knows the public key, right? So he knows this here, right? He knows this here, right? So what he gets S, what Bob does, have to be careful, Bob verify. Bob verifies by, he takes S, right? This turns out to be equal S here in our example. He takes S, and yeah, this is a question. Whoever gets this right, he gets 1 bonus point on the final exam. What does he have to do to get from here to here? What does he have to do? Yeah, last row. Twice. Okay. And then he gets that, and what, this is 1 bonus point. Who wants another bonus point? What does he do with the result? Yeah? Very good. Very good. Many bonus points. You know, I'm kidding. Because nobody gets bonus points here, right? So don't believe me, right? So, okay. Check this here. Okay. So let's do maybe kind of a remark thing here. Yeah. This is like side remark here. So when Bob computes f to the s here, what is s was f to the fifth here, right? You see that? So this is equal to f squared to f to the fifth of r. And because, you know, this is not really well, actually, this is like Potenzierung, right? Like doing regular power laws, right? This is equal to f to the seventh. Okay? So what's happened to this little r thing here, right? It hopped 1, 2, 3, 4, 5 times. This is s. And then Bob adds another 2 hops to it, 6 and 7, and then we end up here. Okay? I like that graphic, right? Okay, so in general terms, so this is for m equals 5. If we have the general case, we have a message with W bits, V bits, and you can say either W can be W for window, but it can also be W for winternets, whatever you prefer. You can make up your own meaning of this. Okay. Then signing in the general case, what do I put here? Here was the exponent 5. What do I put here? Yeah. It's m. Here, you know, this m is this bit pattern, so this is f to the m. Okay. Also, people who I was just about to say that. Yeah, this is really no. It's great. It's much better. It's much more interactive. It's great if you do that. So I was just about to ask, would that make sense if to choose like a nice number W would be 1024, right? 1024 bits, this 128 bytes. Why would that be super stupid here? Because, you know, if W is 1024, then the maximum number, 1024, the m value would be 2 to the 1024 minus 100. This is lifetime of the universe, right? So in practice, m is moderate as in 8, right? You know, like W is 8, right? The window. And yeah, we're going to deal with everything. Okay, so this is good. So this is signing. And now it's getting a little bit more interesting here. I'm leaving a lot of space here. What is the exponent here? How often should I do the exponent here? Any comments? Who wants to? We have one, somebody else. What would be a good number here? Look, you know, here I did 2. How did I end up with a 2 here? Any? You were first. Yeah. Yeah. Exactly. Yeah. Exactly. Yeah. Maybe I should do this. So going from here to here, maybe I should have said this. This takes 2 to the m minus 1 steps. I should have said that for. Again, I'm teaching that for the first time, right? Next year, everything's better. So, yeah. Impossible. What's wrong?
2 to the power of W minus 1 minus 2.
Gut. I'm not there yet. Okay, very good. Very good. Yeah. So, mistake. So, initially, you have to go 2 to the W minus 1. That's why it's stupid W 1024, right? This is lifetime of the universe. 2 to the w minus 1, you end up here, but we want to be here in the middle, right? And that's what the kommilitone said correctly, the student. Here you, now I'm double checking, you're subtracting m from it, the value of m, okay? And you check as before, is this equal to K public here? Okay. Now let's put all of that in a more conventional protocol. So we have Alice. We have Bob, and we do need Oscar now. You will see in 5 minutes, so we need Oscar here. So Alice computes K private is equal to R. Protocol for W equals to 3. Again, we stay with concrete numbers, and I think it's easier to understand. Okay. K public, we call P, is f to the 7th of R. Yeah. And then you send over K public, and Bob obtains K public is f to the 7 of R. Again, example, m is equal 101, binary of 5 decimal. And now if we do signing, S is signature, the signature algorithm, which has as input the private key, K private, but also the message M. Yeah. And this is f to the m of R. In our example, this is f to the 5th of R. I give you a minute to catch up. Now you have to be, yeah.
Would the signatures even provide integrity? Because if Oscar knew the signature for 5, he could easily compute the signature for 6 by hashing it.
We're going to do that in a minute. Very, very good. Excellent. 2 bonus points, okay? Yeah, that's good. He gets nothing, right? But don't tell him, right? Okay, so, yeah. Yeah, so... And now to what we're going, your attack in 3 minutes or 4 minutes, right? So at some point, Oscar is going to intercept here. That's why what I want to write down here is now M, S. Don't put that in the middle, put that on the left, because we're going to do the attack here, right? So it was very good, yeah. Now Bob would like to verify. In general terms, he uses input to the verification algorithm is K public, so this here, M, S, right? And what is the verification? We have an auxiliary, Hilfsvariable, auxiliary variable, which is f to the 7. Where's the 7th coming from? This is the maximum value, right? This is for 3 bits m, the maximum value is 7, right? This is what we did here. F to the 7, now we have to subtract the actual value of m, which is 5 here, right? Of R, stimmt das? Of S, sorry, of S. So this is f square of S. And then Bob checks, is this auxiliary variable, is V equal to public? Okay. There is zero new. This has exactly the same information content that we have here in yet another way of showing that, to confuse you. Not to confuse you, really. I want to show this is kind of how normal cryptography explains that stuff, right? Okay. Okay, so this is great. Let's talk. 1 second. Let's talk about security services. Let's start with authenticity. And what we call authenticity, some books call that sender authenticity. Meaning, if this checks out for Bob, right? If Bob gets the correct K-public, right? And now, assuming this has been distributed correctly, right? I mean, if this is a K-public is from Oscar, everything is lost, right? So we're not talking about that case. So that means the public key has been distributed correctly. If this checks out, does Bob know this comes from Alice, or can it also come from Oscar here? That's my question here. What do you think? If Bob's this public key really he got from Alice, it's not from Oscar. Can this possibly, can Oscar do this type of thing here? No. In order to do that, because how is this computed here? F to the 7, he cannot do it. Bob needs, for the signature generation, Oscar would not need R here, right? You have to hash R. You can't do that. And what you cannot do, given K-public, you can't go here in this way, okay? You can't do. So we have user authentication. What about integrity? What happens if Oscar switches this? And we're excluding your attack for now, right? Let's say if he replaces m equals 5 by m equals 4, that means he goes to this value here, right? Yeah.
It's not going to return the public key.
What's that?
It's not going to return the public key because it's going to be 7 minus 4.
Yeah, exactly. Yeah, you get the incorrect one. It doesn't work, right? If this would be 4, this equation would be 7 minus 4 is 3. Bob would hash 3 times. That wouldn't work, right? We're going to see an attack, sneaky attack. So integrity works, which is great, which didn't work with the stupid protocol we had, right? And non-repudiation. Meaning, later on, Alice said, oh, I never sent this pair M and S here, right? And it's again the same thing, only, and she claims, oh, Bob came up. Bob came up with this value S here, and again, you can show Bob cannot compute S by himself, right? He can only go forward, right? He can go from S, 1 hop, 2 hop, reach K-public. He would not be able to generate S by himself, okay? This is exactly the case with RSA, okay? Good, so checked, all of the check is great, it works, right? But now there was a really good attack. Do you want to talk about this again? Yeah. Yeah. I was sneaky, right? I said, what happens if Oscar replaces 4 by 5, right? That doesn't work, but the other way works, right? So there is, this is now the, I didn't find I called that message incrementation attack, and there might very well be a term used in literature, but I don't know. So Oscar can intercept here, right? And what he can do, this is, I just call that incrementation. Incrementation means hochzählen, right? implementation attack. So he intercepts now, and let's do it as an example here. Example. He computes M prime, M strich, which is simply, to keep things simple, M plus 1 is equal to 6, right? That means this suddenly becomes a signature, right? And that was totally right. Can Oscar, given this, as to the fifth he knows, right? How does he go here? Well, he uses SHA-3, right? He applies SHA-3 one more time. So he can take this S that he gets, and what does he have to do, given S, to compute S prime here in this example? What does he have to do? Yeah, exactly. What they have to do if he increases by 2, what do we have to do at this point here? FF, right? Do it twice, right? But you can only go in this direction, right? You can't go back. But increasing, like, you know, do we have an Hausaufgabe on that, right? Problem, is that right?
Yes.
Yeah. Increasing is nice, right? You know, once you will all become professor, teach cryptography, and this is nice because then you use an electronic transfer, you increase the amount of the transfer. This is cool, right? So this is good. And then he sends over M strich S strich M prime S prime, and it would still check out correctly. Okay, so this is bad, right? But there's a relatively easy fix with this here. Okay, this is bad here, right? This is. Okay. And we're going to. Das war 8, 9. And yeah.
Yeah, so the problem is that essentially we cannot be confident anymore that the message we receive as well as the signature are actually correct.
Right.
If we previously, so on Alice's side, so like we learned in a very simple case about like parity bits.
Yeah.
But even more sophisticated message, which like once again like kind of calculates the distilled down value out of the message, which we also send along, then can that not help with ensuring that?
Exactly, that's what we're going to do. Yeah. We do essentially something like a sophisticated version of parity bits. We're going to do now. Yeah, very good, very good. Yeah. You could probably even, I was just thinking, maybe even compute a hash checksum. They do something different here. Yeah. Okay, so this is now, this is the checksum for Winternitz. Okay, so this is what's called a countermeasure in cryptography. Countermeasure against incrementation attack. Incrementation attack, Doppelpunkt. We need a checksum. Okay. So we're doing some computation, actually very simple computation on the message we're sending here. But we have to be careful, and then what we end up signing is the message and the checksum. But we have to be careful that the checksum can also not be manipulated, right? Cannot be incremented. We're coming back to that. Okay. So these are 3 things we do. So A is split n-bit message in digits. It's kind of what we're also doing here, and I'm jumping a little bit, I do apologize. So up there we did this baby, right? This baby toy example, 3 bits, right? Normally we want to sign PDF files that are whatever, 1 megabyte, right? 1 million. 8 million bits or something, right? So now after the split, we have a digit here, so the M0, M1, up to ML minus 1. So these are digits here. And each digit has W bits, okay? W was 3 before, right? This is our Winternitz parameter, and we talked about, think about it, in practice often W is 8, right? So this is 8 bits, this is a byte, right? So, and actually in digital computers, many type of messages, email, PDFs, they're naturally represented by bytes anyway, right? So this is W, this is W, this is W, okay? So we have n bits, let's say n is 800, W is 8, then L would be 100, okay? You get that? You always use your, your smartphone has a pocket calculator, you always divide by 8, it's really easy. Okay, so L is, this is just for completeness, you take n, you take 800 divided by 8, you get 100 out. Sometimes it works with 800, doesn't work for 803, and here we need this ceiling function, right? You do this aufrunden, right? You divide by W and you do aufrunden. And what is the possible value range? Which values can each of these digits take, right? Here before, we saw that for W equals 3, it's 0, 1, 2, 5, 0, 1, 2, 3, 4, 5, 6, 7. In the general case, we start at 0, blah, 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 blah. And what is the largest number you can represent with W bits? With W equals to 8. What is the largest number? Yeah, and can somebody do that mentally? If W is 8, what is the largest integer we can represent with 8 bits? 1,000 euros if you answer that. Okay, yeah. 255, exactly. 2 hoch w minus 1, very good. Okay, so this is, if you wish, formatting, right? We end up with this long bit file. We separate it in chunks, and these are the parameters. Now we do the important thing, checksum. We compute a checksum. Namely, you do C is the sum, arithmetic sum, running from 0, 0 up to L minus 1. You know the summation symbol, right? Yeah. So it means we kind of touching each of this digit, M0, M1, M2 up to ML minus 1, right? And now the easy way, I have to be careful what I'm telling you, don't copy, you're going to die, don't copy here. The easy way would be that. We're just adding up that, right? But that doesn't work because we want to prevent this incrementation attack. So we have to do kind of, if you increment any of these, C would also be incremented, right? And that would work for the attacker. So now we do a little trick. We take the maximum value, which is 2 to the W minus 1, and we subtract I from it. That's what we're doing. Okay. So if you wish, we take kind of the inverse or whatever of these values here. Are you going to talk about that in the... Why we take the negative here? No?
Maybe a little bit, but...
Yeah, okay. Good, do that in the exam. Gute Klausuraufgabe. Okay. Yeah. Oh, isn't that either Kleingruppenübung or globale Übung? No? We threw that up. Okay, it doesn't matter. Yeah. Okay, so what you get out here is, so you add up values with W bits and you add maybe a bunch of them. So you get more than W bits out. You get, again, a string of digits out. And we assume this is equal to k, right? And this might be a little hard for you to see. K is quite small, right? This is even for very large L's here, this is by no means the length of L. This is small because you're just adding them up, okay? Where again, each of the CIs here can take values from 0 up to 2 to the W minus 1. And then last step, we prepare the input. Prepare input for signing. That's what we're going to do, okay? So what you do, you take your original M, which is this, which is just your PDF file split in 8-bit chunks. You append, anhängen, C. You know, this is a fancy symbol, just put it next to each other, right? There's nothing magical about this. So what this becomes, so this is M0 up to M. Again, this is your PDF file, right? Just your PDF file grouped in 8-bit or W chunks here, right? And then you add these digits here, C0 up to CK minus 1. Okay. Yeah. No. Well, here you pad by zeros. Well, only the last digit you pad, let's say. No, not really. No, I wouldn't call this padding here. I don't think so. Yeah. Ist das eine Übungsaufgabe? Well, you can, what you have to do, this is 2 to the W minus 1 is fixed. It's from 255, right? MI is not fixed, right? MI is a value, right? So for which MIs do you get the maximum value out here? What are good? How do you have to choose all these MIs here so that this summation becomes maximum? What is the smallest possible value for M? 0, exactly. So what you do, you add up L times this here. So the maximum value, very good. So C max is L times 2 to the W minus 1. Okay. That looks bad. It's not really bad because this is, we have already about the number of digits here, and this is logarithmic in L. That's so so roughly speaking, if you have 1024 of these here, you have the logarithm of binary logarithm of 1024, which is 10. So if you have 1000 digits here, or 1024 digits here, you have 10 digits here. This is roughly the behavior here, okay? Because this, you add them up, and adding up is pretty slow, okay? It's actually in the book. In the book, I talk about this very thing. And once you start doing, do we have examples for that? Probably not, right? For the, yeah.
We don't have it explicitly, but we can talk about it.
Yeah, we're going to talk about it. Okay. So, and now, I don't think it's super confusing. It's only a little bit confusing. With respect to signing is we're going to do this type of things here, right? This is going to be our new über M, right? The final M here. So later on, we don't distinguish between this part of the message and this part of the message. We all give them one coherent notation. We call that MC, which is kind of stupid, but I took that from some book. I'm sorry. So, and this is the up to MC index J minus 1. Okay. And again, each of them are W bits wide. Okay. Yeah. Good. Yeah, and now we are ready. Do I have a... I'm lucky. Okay. We do the protocol. Okay, Alice. Alice has to do this stuff that we saw there. Alice has to generate M together with C, which is what we just wrote down. So this is MC 0 up to MC J minus 1. And then she generates keys. Keys is car private is R0 up to Rj minus 1. And I'm going to stop here for a second. Because I'm just realizing this is the first time we're talking about how do you sign long messages, right? All the other baby kram we did, like here, we only signed like 3 bits, right? Now we talk about signing 1 million bits, right? Or something like that. So, okay. So what we have here, message followed by checksum. So each of these W of these 8-bit values, you need one random value, right? So these are all random, okay? And each of these random values are hash f to the W minus 1 times. And that becomes your public key, which we denote by P0 up to Pj minus 1. So what I mean by that, how do we compute P0? Let's say W equals to 8, right? You take 80 and you hash it 250 times, you get P0 out. You take R1, which is also a random number, you hash R1 255 times, you get P1 out, blah, 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 okay? Is that pretty? It's not a big deal. Hashing is very, very fast. And Alice sends to Bob car public, and Bob gets car public just for completeness. He gets a set of values P0 up to P index J minus 1. Okay. And now that was key generation. Now we do signing. Alice takes again MC0 up to MC index J minus 1. And now she does this here, what we have here, right? You take each of these digits, right? MC index 0 is an 8, let's say W equal to 8. It's an 8-bit number. What are the possible, if W is 8, what are the possible integer values that MC can take here, this MC0 here? What are the possible values? It's very tiring. Talking 90 minutes for you, everybody's tired. Which are the values that he can take on here? This is an 8-bit thingy. What is the range? Yeah. Exactly. 0, 1, 2, 3, maximum 255. So what we do here, you take each of these you take, I'm always getting that wrong. You take the Ri that belongs to that, right? You take MC0, R0. So you take R0 and you hash that MCI times here, okay? Depending on this integer value. Let's say this integer value is 113. You take R0 and you hash that 113 times. This is what we did here. M was equal 5, so we hashed that 1, 2, 3, 4, 5 times, okay? And what you get out is S0, S1, blah, 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 up to Sj minus 1. And we call the whole thing S. You send over. M concatenated with C, comma S. So. And here comes now the verify step. So Bob gets a bunch of these signatures, right? Each signature is a signature on one of the digits here. So now the exponent is somewhat messy here. So you do again 2 to the W minus 1 minus MC index I. And he checks, is this equal to Pi for I runs from 0, 1 up to J minus 1. Okay. Lot of material. You do have to do the homework. I need I think 2 more minutes of your time, or maybe 3 more minutes of your time. We're done with Winternitz, hurrah! I know that was a lot of material at the end. Once you do the homework, yeah, you start with you, yeah.
How does the computational complexity of this method compare to traditional ones?
This is kind of hard to say. I mean, first of all, I have to be careful. It's not terrible because you do. I mean, the worst thing, if let's say if W is bound, like something like 8, right? You do a bunch of hash operations, right? But that is, I would say, let me be careful. No, you have 0. You mean in conventional ones, or? No, you have 0. All of these are not exponentiations. They just hash. But you have a bunch of them. So you pay with hash operations. Hash tends to be fast, right? Yeah, hash tends to be fast, right? There was another question, or yeah.
I think I missed it. Is J, K, and E, and I are just the implementation index?
So J is, wo kommt J here? This is a good question. So here we have L, and here we have K, right? And I should have said, and this is J is L plus K. Sorry. Teaching for the first time, right? So you can feel free to criticize me, right? You know, all the videos that you normally watch when they were recorded, that was year 15, right? You know, I started in 95, right? You know, with clay tables back then, right? Tontafel. I'm kidding. And then they were recorded around 2010, so 15 years later, right? So, and I also taught in the US, where I sometimes taught 2 courses per year. So this is for the first time. So I just want to very briefly, and we're totally out of space, very briefly, but these are just 2 keywords. This is not even a proper chapter. Let's just call this attacks on Winternitz OTS, Winternitz one time. Okay. The first attack is, let's call that I, is inverting of F. This is bad. I mean, this is equivalent of breaking AES, right? And you can say, okay, what's the weakness against AES? Well, you break the actual AES, right? You find a mathematical way to compute the key. Much more non-trivial, and this is signature reuse, meaning once you signed a message, with, where are we? Yeah. Once you sign a message involving these random values here, right? They're going to be used here, right? You have to throw them away. Okay, and we're going to talk in the exercises about that. So this is a huge problem in practice, right? This is a little weird, and what is Christof doing with the indices, but it basically works, right? The problem is, with this car public, right? This car public is computed from these values. You can sign exactly one time. This is like one-time pads. This is stupid what we did so far here, right? So every time you sign, you have to send this over, right? So this is not great. We're going to do that next week. Well, in 2 weeks, really, right? So next lecture, we're going to deal with it, how to go from a one-time hash-based signature to a many-time signature. This is based on Merkle trees, hash trees, is vaguely related to cryptocurrency, really cool stuff. Thank you so much for coming. The end of my lecture.